Greetings, everybody. We have a new section to work on today, section 3.4. Still drawing heavily from what we've been doing before, but this time we're going to be talking about parallel and perpendicular lines. All right, so let's get right into it. Hopefully we'll make this another short one to get you on with your week. So let's move us on over here. Relate parallel perpendicular lines for our objectives. And we're going to ask the big question: what are the properties relating lines that are parallel and perpendicular, and how does this compare to what we've been doing with transversals? Basically what we got is a handful of theorems about parallel and perpendicular lines, and I'm just going to present them with a couple proofs and let you get to work on what we need to get to work on, all right? So the first theorem we're going to talk about, Theorem 3-8. If they don't have a better name for it, they just use numbers for it, so your book calls this one Theorem 3-8, and it simply says that if two lines are parallel to the same line, then those two lines must be parallel to each other. For example, if A is parallel to B and B is parallel to C, then A is parallel to C. So again, if A is parallel to B, and that's indicated by these little doohickeys over here, if A is parallel to B and B is parallel to C, then A must be parallel to C. Okay, kind of makes sense, I think. Not too big, not too troublesome. All right, erase that. Move on. Here's our proof. And again, I'm going to leave it up to you. I'll reveal the answer in a second. If you would like to, give it a try proving it on your own. I'll reveal the answer here in just a second. But I will give you this hint. We're going to start with the givens. A is parallel to B, B is parallel to C. We need to prove A is parallel to C. We're going to use what's called an auxiliary line. So the red line here, line L, is something that we've added to the picture just in order to make it possible for us to do the proof in the way we're thinking about it, okay? So I've also added labels for angles 1, 2, and 3, and using those, hopefully you can come up with the proof that I'm about to reveal. So pause it if you'd like to work on it, and then I will reveal in just a second. All right, so here we got to start with our given. A is parallel to B, and because of that, measure of angle 1 and measure of angle 2 must be the same because they're corresponding angles, and for parallel lines, corresponding angles must be congruent. So that's where we got this thing coming from. All right, take our next given, that B is parallel to C. Well, that tells us angles 2 and 3, because they're corresponding angles for parallel lines, must also be congruent. So if 1 is congruent to 2, 2 is congruent to 3, then 1 must be congruent to 3 by the transitive property. They're both congruent to 2, so that tells us 1 must be congruent to 3. Now, if 1 is congruent to 3, here's our last little trick. If 1 is congruent to 3, then we can basically ignore 2 and all of its parts, and we can see the corresponding angles formed by 1 and 3. By the converse of the corresponding angles theorem, if those two are congruent, which we said right here, those are congruent, the lines must be parallel. There's our conclusion. All right, makes sense? Let's move it on then. Theorem 3-9. In a plane, if two lines are perpendicular to the same line, so both A and B here are perpendicular to C. If two lines are perpendicular to the same line, they must be parallel to one another. A is perpendicular to C, B is also perpendicular to C, therefore A and B must be parallel. And basically the proof is simply involved in the fact that two congruent angles, these angles have to be congruent by definition of perpendicular. They both must be 90 degrees. Therefore A and B must be parallel. Again, if corresponding angles are congruent, the lines must be parallel. That's the converse of the corresponding angles theorem. Okay, next, Theorem 310 does have a name. That's the perpendicular transversal theorem. And this says that in a plane, if a line is perpendicular to one of two parallel lines, it's got to be perpendicular to the other as well. There's a typo there. Let's fix that. All right. If a line is perpendicular to one of two parallel lines, then it's also perpendicular to the other. So in other words, if A is perpendicular to C and A is parallel to B, then B and C also have to be perpendicular to each other. Basically, our proof is simply that corresponding angles must be congruent. So if these lines are parallel, which they are, the corresponding angles formed here and here must be congruent. Therefore, line B must be perpendicular to line C. All right. Next, here's a proof for you to work on. In a plane, A, B, C, and D are lines such that C is perpendicular to B, B is perpendicular to D, and D is perpendicular to A. What can we prove about C and A? All right. I don't know about you. I can't get my head around it. I'm going to let you pause it now if you'd like to try the proof totally on your own. I'm going to draw a picture for you here in a second and then reveal the answer, but if you want to go ahead and do it on your own, pause and then we'll get going. But in the meantime, let's go up here and draw some pictures. All right, so I'm going to start with line C. All right, there's line C. Then I'm going to draw a perpendicular line B. All right. Good. Now, C is perpendicular to B. Now, B is perpendicular to D, so let's draw another line for D. Right there. And it doesn't matter, again, where we draw it. This is just giving me something that my head can wrap around. So there's D. D is perpendicular to A. So let's draw an A that's also perpendicular to D. So it must be something like this, right? There's A. All right, so now can we prove that C, if we carried it on over here, must be perpendicular to A? All right, so we know the relationships that we formed in various spots. C is perpendicular to B, B is perpendicular to D, D is perpendicular to A. Now, can we also assume that that angle right there, C perpendicular to A, is going to be true? Of course we can. Here comes the answer. Right? C is perpendicular to B and B to D, that's given. So these two marks here and here are given to us. Therefore, by theorem 3.9, C and D have to be parallel. Not something readily obvious, but they've got to be parallel, because theorem 3.9 told us that if two lines are perpendicular to the same line, they must be parallel to one another. Both of these are perpendicular to B, they must be parallel to one another. Now we go to our last given, D is perpendicular to A, and that tells us, of course, that C must be perpendicular to A, and that's the perpendicular transversals theorem, which says that if a line is perpendicular to one of two parallel lines, right, C and D being our parallel lines, okay, if a line like A is perpendicular to one of them, it must be perpendicular to the other. So there's our proof. All right, fairly short and sweet. Write a good summary. I'll see you guys later.